All right, thanks very much. Can you see my screen? You got my slides there?
Yes.
All right. So thanks everybody for coming to this, and thank you for the organizers for selecting our paper and for having us. I'm going to jump right in. As you mentioned, this is joint work with my colleagues Jared Murray and Carlos Carvalho at University of Texas. So we are going to talk about a Bayesian model that we developed over the last several years. And we're going to try to motivate it and explain sort of how we think about this basic problem. So these days, this problem is pretty familiar. Just to lay the groundwork, we're going to be considering continuous outcomes. We're going to consider the case where we have a binary treatment, treated or not treated. We're going to have observational data. So this is not data from an experiment. We're going to assume, though, that we do have all of the covariates that we need. Okay, so that's going to turn this into a regression problem, although a hard one. We're going to be using nonlinear supervised learning techniques. Our interest primarily is going to be conditional average treatment effects. So what is the treatment effect for an individual of a certain type as described by those covariates X? And one thing that distinguishes this, and to some extent because it's Bayesian, but just for practical reasons, is we care about finite sample performance. So we're going to be really interested in how these things do in realistic size samples. So here I just got the notation. Many of you are probably familiar with this, it's old hat. But the idea is that given X, which is what I'm going to use to denote our covariates, our control variables, the potential outcomes are independent of treatment assignment, which I'm denoting by Z. And we're going to assume that we have overlap. So we're going to assume that everybody in our sample, all of those Xi's, have some positive probability of being treated. So in this setup, which is like the easy one in some sense for causal inference, it reduces the problem to a response surface inference problem. And so we're going to be interested in conditional expectations. And machine learning is good at conditional expectations these days. So we're going to denote tau is going to denote our treatment effect, tau of X for individuals with those covariates X, and it's going to be a difference of these two conditional expectations. Of course, I guess the challenging thing here is that F is not known, and it might be quite complicated, and X might be high dimensional. All right, so one way that, when we first came to this, the question became very quickly about priors on treatment effects.
Richard,
so
1 second.
Yes.
Someone mentioned that the slides do not move. I wanted to make sure, is anybody else having the same problem? If anybody can type in the question and answers if they are.
And Michele, you saw it move, right?
I saw it move. They moved for Georgia. Okay, it looks like they are moving for most people.
Okay.
Sorry.
No, thank you. So we started thinking about regularization, and the way that this happened was we have some other work on shrinkage priors and linear regression, and we would run the linear regression to do treatment effect estimation in that context, and we were getting really biased answers. So we started thinking carefully about what do our various models imply about the amount and degree of regularization on the actual treatment effect parameter. So, to foreshadow where we're going with this, our first contribution, or our first idea, and we're certainly not the first to have had this, but we were motivated, I think, by distinct reasons, is we're going to want to use this representation up at the top. So we're going to have a function mu and a function tau, and tau is explicitly going to be the treatment effect. It's going to be the offset from mu when z equals 1. And to motivate this, and really my goal today is to help you understand sort of why we wrote the paper. What we did is we started out thinking about the two standard ways that we might do this. So on the left here, we have what we call the separate regressions method, which is just that we take our treatment data where z equals 1 and we fit a nonlinear regression model. And then we do the same thing for the control arm. And then we estimate those functions f1 and f0, and we take that difference, and that's how we get our treatment effect. The other thing that we could do is we could treat z as just another covariate. and we could do a supervised learning method and try to learn one response surface, which I'm denoting here F, and X and Z are sort of treated the same, and we just put them in. In the context of BART, which is a particular supervised learning method that I'll talk about later, it was suggested in 2011 that we could take this approach and that it worked pretty well. And indeed, it does work relatively well. But what we noticed in our personal experience was that both of these things had some liabilities. So what's the problem with the independent regression approach? Well, essentially what happens is that you're not putting any direct regularization on the difference between those surfaces. And if you put independent priors or independent penalties on F1 and F0, then a reasonable function on F1 and F0 can sort of compose via that difference operation to give you a function that's more complicated than either one individually. And this is not rocket science, we have a little cartoon picture that shows it. But what it means is that when you're doing this, you don't have any fine control over the treatment effect. And in particular, you're basically saying that you think the treatment effect is going to be more complicated than either of the potential outcome expectations. And we think that in most problems, that's not realistic. This is a problem that applies generically to this parameterization, and it's going to be a problem for any model that has independent priors or penalties over F1 and F0. On the other side, if you just model it as a single response surface, in that case, you actually do have some sort of dependence between those two functions that you're trying to estimate for the different values of Z. But often it's implicit. In the case of BART specifically, it was hard for us to understand. And even in the case where you have a Gaussian process, picking the covariance function that operates on X and Z is sometimes, we argue that it's difficult to understand. And again, the fact that you don't have a direct way to vary the regularization on the treatment effect is a problem that's generic to this parameterization. And so we think this parameterization is hard to work with. Later on, I'm going to show you some comparisons between these three, and hopefully you'll see what I mean more concretely. So for this particular problem, in simple models, there's a common solution, which is just that we want to parameterize by the difference. So here I have a very simple IID normal model, the sort of thing you'd see in a textbook. And it's very common to have a situation where you don't know much about mu1 and mu0, the means of your two arms, the two groups. But you might know that you expect them to be similar. And so if you parameterize by the difference, you can codify that by saying that the prior on tau should be shrunk towards 0. And it just turns out that this is convenient and it's kind of uncontroversial, and people recognize that it's a generally good idea. So we're just going to do the same thing. So we're going to apply the same intuition to the nonlinear regression case and use the representation at the bottom, which I mentioned before. But if you do that, you have to write new code because that parameterization is not sort of the standard one. By the way, you might notice that I'm not using the same X in tau and mu. And that's because when you write it down this way, you might want to specify different variables as effect moderators in the vector W. So, and I already said some of this, but we think that the virtues of this treatment effect parameterization is that we can explicitly regularize treatment effects to taste. Okay, some problems you want them to be maybe very heterogeneous, others you might want them to be very or nearly homogeneous. But you don't lose any generality. This is just a way that you can represent the treatment effect and this is just a way that you can represent the potential outcomes in this framework. And as I mentioned just a minute ago, a really important thing in practice is that it allows you to have distinct sets of variables as moderators. And when you do either of the other two approaches, that's really just not possible, at least not without a lot of extra work. The second idea, I think, in the paper is that we introduced the idea that the propensity function can be an important covariate transformation, all right? And that's the way that I would encourage people to think about it. So the idea here is that if we have some idea of what the assignment mechanism is in terms of X, so the probability of being treated given X, then we think that including that as a transformed variable into your regression model directly has certain virtues, all right? And you can do this in any model, and I'll show you that we can do it in either of the two parameterizations that we showed you. But specifically in the treatment effect parameterization that we use in BCF, the Bayesian causal force model, it looks like this, which is where we have the pi hat of x shoved into mu as an argument. And that's sort of like the crude way to think about it. So why do we think this is a good idea? The reason we think it's a good idea, well, the first one is that we tried it out and it sort of did what we wanted it to. But if you want to motivate it from practical considerations, I think this idea of targeted selection is really powerful. And the basic intuition here is, just to take an example, doctors treat the patients who they think need it. All right, so if we have a non-random treatment assignment mechanism, one mechanism that this might be non-random with respect to is that doctors are trying to only treat the patients that they think are in need of it. And what does that look like? That just means that the person or the process that's giving rise to who does and does not get treated is trying to attend to what the baseline potential outcome would be. And I want to emphasize here that this does not need to be exact. And furthermore, it's not the actual potential outcome that we're conditioning on here. It's the expected potential outcome given X, okay? So there's nothing illicit going on here in terms of conditioning on actual potential outcomes. So what are the implications of this sort of thing? So what it means is that the probability of treatment is liable to be an increasing, or decreasing function of the expected outcome under no treatment. And of course, this applies more widely than just the medical context that I mentioned. We don't think it always happens, but we think it happens enough that it's worth thinking about. And so we started thinking about what are the implications of this idea for inference or estimation. Like if we're trying to learn treatment effects and this sort of selection is happening, do we need to worry about it? So the picture I want you to think of is sort of like this. In terms of the parameterization that I've laid out, we have the propensity function pi, and we've got the prognostic function mu, which is the expected outcome under no treatment. And then we might have data that looks like this. And treated is orange and untreated is blue. And you can see we've got plenty of overlap, but you see a general trend. And the general trend, of course, is what I just described. The reason it doesn't lie exactly on the line is that in the way that I generated this data, the doctor doesn't know exactly what mu is, and so it's noisy. Nonetheless, there's this trend. What is the implication of that trend? So on some level, this is just the usual confounding. But here's the problem. When I show it to you like this, it looks really simple. But as a matter of fact, X can be dozens of variables, and mu of X can be quite complicated. All right? And here's what happens, we argue, is that if you flip this picture on its side, it's the same exact plot. You can see that near monotonicity of pi in mu means near monotonicity of mu in pi. And what that means is that if you're trying to learn a complicated function of x, mu, and it depends on pi in this particular way, if you knew pi, or an approximation of it, that would be a really good dimension to know about when you're trying to learn this relationship. And that's important because if you don't get a good estimate of mu, you don't do a good job deconfounding. So having x is theoretically enough, but really we need to learn mu of x. And if we only have finite samples, we want to make it as easy as possible to do that. So here's what happens. If mu as a function of x is complex, however we want to define that, it could mean that it has lots of wiggles, it could mean that it uses lots of variables, however you're parameterizing complexity. If mu is complex, under targeted selection, pi and mu are going to look alike in the sense of this picture. They're going to be sort of nearly monotonically related. And what that means is that misattributing mu to the treatment effect can yield a pretty good function fit. All right. And what I mean by that is if you visualize here just classifying based on the orange and the blue, you're going to pick up a lot of that same signal, right? Because there's a pattern there because Z is assigned according to pi. Here's where that becomes a problem. That becomes a problem if that response surface is much simpler than the mu surface, because we're doing nonlinear models and we're regularizing, and we have to because the world is complicated. But if you don't attend to this distinction, essentially you'll get a bias treatment effect. So we call this regularization induced confounding. It's not actually confounded because we've satisfied all the assumptions of strong ignorability. Nonetheless, in finite samples, you see it persistently, that if you generate data according to targeted selection, you reliably produce finite sample bias. in a way that ruins your inferences. And I'm going to sort of stress, just like I did another point, that this is not specific to the tree models that we use. It would apply to any notion of complexity penalties, all right? And the problem is that if mu is complex relative to that penalty, then and the response surface you can get by attributing it to z, misattributing it, this is what's happening. Okay, so having laid it out that way, the solution might seem obvious, and I actually already told you what it was. But the idea is we need to make it as simple to deconfound as it is to attribute it to treatment. And so one really straightforward way to do that is to think about including pi hat, an estimate or an approximation really of the propensity function, as an explicit feature. And one thing that you can do, an analogy here is that we're rotating our parameter space, we're rotating our covariate space so that the dimension along which we're penalizing includes this one, because this is an important dimension, and in fact, it's the deconfounding dimension. So we want to make sure that that we allow the deconfounding to sort of be easy to find, and easy in this case at a rough level means one-dimensional, right? If X is many, many dimensions, and then we include this as a feature, we make it very easy to deconfound. And it seems to work. Okay. So when we put these pieces together, what we get is that we recommend using the treatment effect parameterization, and we recommend including an approximation of the propensity function as a covariate in our mu function, in our prognostic function. And to implement these insights, we need to go a little further. Specifically, we have to specify non-parametric priors over these two unknown functions, and we have to choose a distribution for the observed response and stuff like that. We make some choices there. I'm not going to talk much about the response model. In the paper, we talk about additive homoscedastic Gaussian errors, which is not an assumption that we love, but it seems to work relatively okay. On the other hand, the non-parametric priors, we do have some strong feelings about. And what we use is we're going to use BART, and we're going to think about BART as a prior over functions. So what is BART? I didn't include the reference here. So there's a 2010 paper in Annals of Applied Statistics by my colleague Rob McCullough and his co-authors Hugh Chipman and Ed George. And they came up with sort of a Bayesian additive tree model. What I mean by that is that it represents an unknown function f as a sum of regression trees. And by a sum of regression trees, I mean that there is a bunch of decision rules based on x. And for a given covariate value, you end up in a leaf node in one of those trees. And that leaf node contributes a term to a sum. So we're here in this notation, we're going to have L trees. And each tree has a set of parameters associated with the leaf nodes. And G just maps from the leaf nodes back to the level, the mean level. And that's how we build up our response surface. If you think about this, though, as a prior over functions, they take this representation and then they put priors on the pieces of that representation. And the pieces in this case are the trees and the parameters. And the joint prior on those pieces is the trees are given an independent process prior. And by a process prior, I mean they think about building up the trees sequentially as a sort of stochastic process. And in particular, they say that the probability of splitting at depth d has this nice convenient form. And that implies a particular a prior over any tree. And it's parameterized by two hyperparameters, alpha and beta. Okay, alpha governs how likely you are to split, and beta determines how much you're penalizing deeper trees. This has been used. I'm not going to talk about it much here. If you're not familiar with BART, you should check it out. It's an interesting model. And then the second piece is that we have these priors on the leaf parameters, which are going to be independent with a fixed variance v, and that's the BART model. So what are the virtues of the BART prior, if you think about this as a prior? So first of all, conditional on the trees, it's actually a Gaussian process, because the covariance between any two observations is going to be a function of how often they're in the same leaf nodes. And so conditional on the trees, this is sort of a nice, easy process to study. So integrating over the unknown parameters, it's a Gaussian process. So what we're doing when we learn the trees, though, is that because we're estimating them, we're learning a covariance function, which is really nice. And the learned covariance can be non-stationary and it can be anisotropic. And so it's much more flexible than, say, squared exponential covariance function. Smoothness, on the other hand, can actually be modulated by the number of trees in the sum. As we include more trees, it's sort of a smoother function. It's never smooth in the mathematical sense, but the step functions have more steps. A prior can be placed over the leaf scale parameter in a nice way, and computation is not trivial, but it's pretty tractable compared to similarly flexible methods. So there's a long track record of it working, and we built our work on Jennifer Hill's 2011 paper, and so this is what we're going to use, and this is kind of what we advocate, although all of the ideas that I mentioned to you before would apply to any model that you prefer. So let's pause there and see if anybody has some clarifying questions, because the next part of this is going to be some demonstrations.
Thank you, Richard. So we have a question. Do you have a preferred way of estimating p hat? For example, should I use BART to estimate it, or just a good old logistic regression?
So I certainly don't recommend logistic regression, if by that you mean a linear logistic regression. The implementations of BART based on the probit link that are available, I actually, that's not my first choice. Jared and I have worked on some modifications of that, some other classification models that are BART-like. But generally speaking, we would say that that we don't have a preferred option, but something that is flexible, right? I mean, we want to use supervised learning, machine learning sort of techniques at that stage as well.
We also, another question, how do you pick the prior parameters on BART?
Prior parameters on BART, there are some, okay, so how do you pick them? So it depends a little bit. So thank you for that question, because it allows me to emphasize something here. So we have two independent BART priors on mu and tau. And so one nice thing here is that we can set them separately, right? So we can put stronger priors on tau than we do on mu, for example, which is sort of our default. In general, the V parameter is pretty easy to set or to learn even with a hyper prior on that. L is going to dictate the smoothness, and alpha and beta are going to dictate sort of how big the trees are. So what I would say we do in practice is that we do a lot of prior elicitation by looking at draws from the prior and seeing if those functions look like we want them to. The defaults are pretty good for most empirical applications we find. And so, the first thing we do is just run it out of the box. And then we customize it to particular problems based on essentially smoothness and complexity considerations. It's more art than science, for sure.
Okay, so there are two questions that are related, and I will leave them right now. I mean, I will ask you them, but if you prefer to answer later, let me know. So one is, how does BCF handle covariate imbalance? And the other one is, conditioning on propensity scores is a way to achieve covariate balancing. What is the relationship between regularization-induced bias and covariance imbalance? Can we think of a conditioning on propensity score here as achieving some kind of covariate balancing?
So the covariate balancing is achieved by the direct regression. We are not obliged to include that as a technical condition for identification. And that's, I think, what distinguishes our work from previous work on double robust estimators or balancing based estimators. Nonetheless, we are saying that you need to be able to calibrate the regularization, and that direction in covariate space along the propensity function is an important one that you want to essentially regularize less than other directions. And so it's subtle. I think Jared will have some more to say about this question, but it's very important that we don't need it. We don't need it, right? Like, conditioning on X is enough. But we are saying that regularizing in terms of that covariate transformation leads to better finite sample performance. So it's really hard to think about notions of balance and identification considerations in finite samples.
Perfect.
Yeah, so
Perfect, thank you.
maybe
So
we can clarify that some more later too.
perfect. I will let you go on, and we continue later with other clarifications.
Sure. Okay. How am I doing on time? Anybody know?
So it's
Nobody knows.
28, so you have probably around 20 minutes still.
Okay. Okay. All right. So those are what we consider to be the big ideas. Like what I'm going to show you now is I'm going to actually spend some time looking at a little simulation and try to walk you through the way I think about these problems and how we developed this, because I think it's pretty idiosyncratic in that I think about these problems almost as a scientist more than a mathematician, for sure. So we've got the math and we've got the theory to guide us about what we need to satisfy. But when we're studying black box complicated models and we're interested in finite sample performance, we basically want to do experiments. And we want to run experiments carefully to understand these algorithms. So, you know, what I'm building up to is, does BCF work? So does this model that we've, you know, I just motivated it, but does it actually work? So let me tell you a couple of things. So if the model and prior are exactly spot on, then Bayes estimators minimize Bayes risk. So sort of in the background here, we have this idea that if we get it exactly right and we're interested in repeated use over nature's prior, then all the usual stuff holds. We don't think that, though. So that's not that compelling. The existing theory on BART is encouraging, but it's incomplete. It hasn't been tailored specifically to treatment effects. It hasn't looked at the regularization methods that we are proposing. And moreover, it's asymptotic. And it doesn't, apparently it does not tell us much about how things work in finite samples. On the other hand, in a wide array of simulation studies, we tend to outperform our competitors by a variety of criteria. And when I say a variety of simulation studies, I have in mind the Atlantic Causal Inference Conference data analysis challenges. I believe there have been 3 of those, or 3 or 4. And as well as a couple, like our own simulation studies, and then at least 2 or 3 other papers that have sort of done bake-offs in simulated data. And BCF doesn't ever tend to do badly, very badly, and quite often it's the best performing method. So the question is, like, how seriously should we take this? What do we actually learn when we do a simulation study? And I guess the perspective, since I have a big old audience of 150 people, I want to suggest the idea that if we do our simulation studies carefully, that they can be a very powerful augmentation to our available theory. But you have to be very careful about how you do them and think about what they're telling you. So I'm going to get on my soapbox a little bit. And I want people to think about it in terms of simulation experiments. So what should an experiment do? Well, so first of all, we should state at the outset what question it means to address. Are we trying to show that one software default is better than another? Are we trying to show that a particular penalty is better than another? Are we trying to show that it works well in the real world, whatever that might mean? So we should state that. And then secondly, we should provide a rationale for why the data generating mechanism that we're using in this study is going to help answer that particular question. So it's not about picking a method, it's not about picking a simulation study that highlights your favorite method, which I think happens all too often in the literature. Instead, we want to ask specific questions and figure out what we can learn. Is it going to be a theorem? No. Is it going to be valuable? We think so. So, for example, a simulation study might be suggestive of real-world performance by using data-generating processes designed to be representative of the data we're likely to observe in practice. This is sort of closest to the way that a sort of traditional Bayesian might think of it. Like if you develop a model and a prior and you generate from that prior, you know that you're going to be doing well on those. So what I want to mention here, though, is that these days we've got methods that seem to work better than model-based stuff. And we can ask the same question of those methods, like how do they work on DGPs that we think are realistic? And we like this because then you can have a perfectly civil discussion with people about whether or not the DGP is realistic and in what ways it is not. And I think that's useful. So we did a lot of that in our paper. It can provide an understanding of which aspects of a method drive the success or failure. So I like to do this a lot, which is that I like to take a DGP that's reasonable and I like to push it in various directions and try to break my favorite methods. finding out where that threshold is experimentally can be really useful in telling you what's going on, and it can suggest avenues for theoretical study. On the flip side, you also want to distinguish between families of DGPs where a method performs well and they perform poorly. So one thing I see over and over on this point is it's very easy to accidentally generate data that is super easy, in which every method basically does fine. And it's very easy to generate methods that are way too hard, so the signal to noise ratio is really poor, and then no method does that good. And so the most interesting DGPs, in my opinion, are the ones that are sort of in that sweet spot, which is that they're easy enough. Some methods do well and others do not. And again, what makes this an experiment? Why do I use that word? Because we want to decide what factors we want to vary about the DGP and about the methods. And we want to try to make everything else the same. So hopefully I'll have a little bit of time and I can show you how that looks. So specifically, on the issue of realistic causal DGPs, we pay attention to 5 things in our causal DGPs. So the first one is we look at the magnitude of treatment effects relative to the response surface level. So in our notation, how big is tau, or the extremes of tau, relative to mu? Essentially what we find there is that if tau is huge as a proportion of mu, then you're going to find it really easily relative to any method, because there's essentially no confounding, in the sense that to the extent that there is confounding between mu and tau induced by the regularization, it's going to be small because mu is small. We look at variation in the treatment effects, so that's looking at tau. How crazy is tau? I've seen DGPs that purport to be causal where the treatment effects vary between -100 and 100, which would mean sign switching, and then they're an order of magnitude bigger than the range of mu, right? What does that say? That says that the treatment effect is the dominant thing governing the outcomes. The signal to noise ratio of the outcome data, so how hard is the regression problem in general, that's easy to handle in additive error models, which is what I've played with a lot. But you can do it in other models as well. And that's just looking at like how hard the problem is. Likewise, the other angle of that is complexity of functions, as measured by tree splits or function spaces or number of basis functions in an expansion or something like that. And then strength of confounding. And strength of confounding in our experience was the hardest one to get a gauge on. And really targeted selection is the one trick that we can think of that helps us in nonlinear problems calibrate the strength of confounding. And you can see really interesting things. So if you look at these 5 things, those give us some knobs. And if we attend to those, what can you do? So you've got the magnitude of the treatment effects relative to the response surface, so plot it. You've got variation in the treatment effects, plot those. For the signal to noise ratio, a thing that I like to do is I like to set the error variance as a fraction of the variation in sample of the noiseless function, right? So that way you can figure out your error terms, your sort of noise, and make sure that the fuzz isn't way bigger than the undulations of the function. The complexity of the function, it can be quite hard. And one thing that I like to do is I like to use what's called a single index model, because it allows you to have multivariate functions that are quite complex and difficult to learn, but it allows you to plot them by plotting the inner argument, which could be a linear regression or a simpler like an additive function, basically. So nonlinear transformations of additive functions, which is sort of what neural networks do, right? Compositions of functions. But that allows plotting. And then strength of confounding, I like to develop a targeted selection sort of framework, and then, in other words, pump that mu, that noisy estimate of mu, into a logistic link with an intercept and a slope. And by varying the intercept and the slope, you can vary the strength of the confounding. So we do these things and then we play with them. And I think if you're developing models like this, that it's very instructive, even if you don't put them in your papers, to just help you learn about how your algorithm is working. So what I'm going to do now, hopefully it won't take too long, is I'm going to switch my screen and I'm going to run through a little R script that I have and just give you a real quick example of what this looks like. And for those of you that aren't R native, I will narrate what I'm doing. And hopefully it won't be too boring. I'm going to try to take advantage of the Zoom technology. So I want to go to RStudio and share that. Can you guys see my screen?
Yes.
Okay. So let me just source this code real quick. And it takes a sec because BART takes a little bit to run sometimes. And I've got this panel of plots here. And the first one is that I am looking at a function of mu. So mu is just a function that I designed. You can see what it looks like in line 8. It's ugly. It's essentially based on two trig functions, and then I am multiplying that by a bell curve in order to give it one hump. There's nothing specific about this, right? And in fact, nobody could figure out what this was really, but the picture is all that matters. So I look at the picture and I say, okay, that's what my function looks like. I'm plotting it in terms of an x variable, but what I'm actually going to feed into it is a sum of two independent covariates, x1 and x2. On the other hand, here is the treatment function in the second plot, and the treatment goes from 1.5 to about 3.5 relative to the variation in mu, which goes from 5 to say 16 or 17. So that tells me, just by looking at that visually, I can tell that tau is sort of not preposterously small and not preposterously big relative to the prognostic function over here. I also like to look at histograms of pi, the actual treatment assignment probabilities, and that tells me whether or not I've got extreme selection or not very much selection, and in particular, it allows me to see the range of it. I look at the size of my errors. So here's a histogram of my error terms on the response model, and they range between -1 and 1, which is pretty small relative to the variation in tau and the variation in mu. So then what I'm doing is I'm fitting 3 different models here. I'm fitting the F1, F0 independent BART model. I am fitting the just another covariate version of BART, and I'm fitting BCF. And I'm fitting all 3 of those with and without the propensity function. And in this case, I'm feeding it the true propensity function because I want to hold constant that estimation procedure, right? I'm just going to say, let's assume that we actually know that function. And then I'm plotting the estimated taus versus the actual taus, which is a function of x1. And you can see in this particular, and then down at the bottom here, I've got the root mean squared errors. So what you notice right away is that adding the propensity function in this case really helps. And you can also see that in this particular problem, regular BART happened to do the best. This is just one iteration of that. And so, unfortunately, I don't think I have the time to go through lots of different variations, but let me point out to you the knobs that I would vary. So right here is just a multiplier on my mu function. And so that's going to change this function in the upper left panel, and it's going to make it smaller or bigger. Okay, and then that's going to change how easy it is to tell tau from mu, or how important mu is relative to tau. And that's going to change the performance of the methods. And in particular, what you see when you do that is that including the propensity function doesn't help as much anymore. It still helps a little bit, but it doesn't help as much. Why doesn't it help as much? Because the confounding impact is smaller. So even if I get it wrong, it just doesn't, the sort of extent to which it can ruin my inferences is not as much. On the other hand, I can modify the strength of confounding by taking this slope parameter in my logistic confounding model. So what's my confounding model? I take the true function mu, I center it, I add a little bit of noise. So this is the doctor trying to guess at what his, at the potential outcome under no treatment. And then that goes into a logistic link with this parameter lambda. So if I make lambda smaller, and I source the code, oops. That is not what I wanted to change this one. This is the problem with live coding. There we go. So if we make that small, then that means that the selection is not that strong. And if you look at what that does, you can see the impact on the pies. Now everybody's treatment is narrowly in between 0.28 and 0.36, and that means that there's not a lot of strong selection. When we do that again, we see that the deconfounding impact is not that big. The difference between using the propensity function and not is smaller. And then there's the noise level here, which is I can make the noise really big, and the methods will hopefully get worse. So you can sort of test and probe your understanding of which factors of the data generating process are impacting particular methods. And we think it's a powerful technique that doesn't get a ton of play. Maybe it's because it's hard to publish about, but we find it very instructive. And that's sort of, people ask, why do you think BCF works so well? Because we've done a lot of this. And we've done a lot of this on data generating processes that we think are plausible in the sense of not being absolutely crazy, of having super, super strong confounding or crazy big treatment effects. And it seems to work well. So we think that it's calibrated to the real world, and that's a point that we can all argue, but being explicit about it, it helps that argument be productive. So I think I'm gonna wrap up there. Thanks everybody for coming. It's a great group, and hopefully this wasn't too inscrutable. So thank you.
Thank you, Richard. Okay, so I will leave the questions to the end. There is only one question that may be pertinent to the last thing that you showed. And it is about the R simulation. We have an
yeah. Oh yeah, I have a link. Did nobody dropped that yet? That was my fault. So the slides and the links can be found here. And let me make sure I give this. Can I give this to everyone?
I think so. I will double check also.
Yeah, I apologize. Okay. I meant to share that beforehand.
That as reply. Perfect. Okay, great. Thank you so much. Okay, so as it is tradition in the BA discussion webinars, now we're going to give the word to the invited discussants. We had also a number quite high of contributed discussions. We typically invite open discussions to the discussion papers in Bayesian analysis, and in this case we had a very good turnout. So the paper should be updated with the contributed discussions, all the invited discussions, the rejoinder on the website, I think later today. So I would invite you to look at the paper online later on with the updated rejoinder. The first discussant will be Arman Oganisian from University of Pennsylvania, and Jason Roy from Rutgers.
Great, thank you. So I'll share my screen here. Just take a second. Okay, so hopefully you see the slides, so let me know if you don't. And so this is Jason Roy, so I'll start, I'll do a couple minutes and then Arman will pick up from there. So we'll cover a few of the topics that we covered in the discussion, but we won't be covering everything due to time constraints. I want to first start with a few general comments. And overall, we really enjoyed reading this paper and thought there were a lot of good insights, or not just their main method that they proposed, but we thought throughout there was really interesting insights that they contributed. So I think it's valuable work, regardless of whether you think this is the best method or not. I think it was really well written and very interesting. So we appreciated that. And a couple of things to point out is we liked that there was this clear discussion of regularization induced confounding in this non-parametric context. So there was previously a paper, a few years ago that introduced this idea of RIC, but it had to do with high dimensional data, we have a lot of X variables. But here, the regularization is really more in the fact that you have a highly parameterized model, you're doing this non-parametric modeling. So I thought that was really nice. And they have some nice illustrations of why targeted selection can be problematic, if you don't include the propensity score, And I think they also proposed that a couple of different BART functions, BART priors that you can use for different amounts of regularization. So I just said I wanted to start here with just this main idea. One of the main ideas has to do with this sort of single function kind of, this writing it as a single model instead of as stratified. So I mentioned here that it might be tempting when you have multiple treatment groups to just stratify, fit these functions, and then you can then use the whatever covariate you're interested in and do the contrast to get a causal effect. So it's really tempting, I think, to just stratify and use off-the-shelf priors on functions and get a causal effect. But as was mentioned, you lack having direct control over the prior for causal effects. So if you put priors on these stratified functions, then it's implying something about the prior for the causal effect, but it's not clear what it's implying, and you don't have the same kind of direct control. So the single function, or I'm calling it a single function, but it ends up being a sum of functions here. But writing it as a single model was really nice because, as they mentioned, and as I mentioned a minute ago, you might want to have a different amount of regularization on these two functions. So, for example, your prior belief might be that the sort of effect modification terms might tend to be small. You might want to tend to shrink them to zero because your prior belief might be that interactions are not going to be very big. That's just one hypothetical. You might have different prior beliefs. Whereas this other function here, the mu function, you might want it to allow it to be a little more complicated and not shrink to zero. So we think that's really nice that this single model kind of formulation, and mostly because you can then put a prior on the things that you actually care about. And so you can really think about how you want to do that. So you could sort of start with this function as what you want, using this model that they proposed, and then you can specify priors over these functions, mu and tau. So you could, at this point, you could use a parametric model for mu and tau, or you could use you could use a Bayesian non-parametric approach and have some prior over these functions. You could use a Gaussian process, or you could use BART as they did. But they're proposing something more specific. So they're not just saying do whatever you want up here. They're actually saying, with Bayesian causal force, use this particular form where you're including the propensity score, in this mu function, and then they're using BART priors for mu and tau. And so one of the questions is, I guess there's a couple questions. So is BART the right choice for these? When would it be? When wouldn't it be? And then also, why include the propensity score, or when would that be beneficial to include the propensity score? So here's, we talk more about that in the discussion, and we also we'll talk a little bit about that, some of these points as well, in the next couple of minutes. So here's we just simulated data from using one of their data generating approaches from their simulations, and this shows the true propensity draws of the true propensity score versus the true prognostic score in the case where there is targeted selection, where the treatment probability depends, heavily on the prognostic score. So you see this very nice monotone relationship. And so if that's the case, if this is reality, it certainly helps you, to use this pi hat here because, you have this nice monotone relationship between the true mu and pi. And so and later in the paper, they call it a hint function, and that's kind of what it is. This pi hat is sort of steering you in the right direction. But one question I think we have is, how often does this happen in practice where you have targeted selection? Because, you would hope, most of the problems I work on are more clinical health data related questions. And you would want, let's say, a clinician to be making decisions based on the expected benefit of treatment, not on the expected value of Y0. As we've mentioning here, like if you think of Y0 as how frail a patient is, hopefully they're not making a treatment decision based on how frail they are, but rather whether they expect the difference between whether they're treated or not to be large, to where it'd be beneficial. So I think there's a question to me on how often this occurs in practice, at least in the kind of problems that I work most closely with. So I have some some degree of skepticism on whether this is very common where you would have sort of strong targeted selection. But I think, in cases where there's reason to think that this approach would be beneficial, certainly. So I think we'll move on to Arman now to continue this discussion. And I'll stop sharing.
Okay, hi everyone. This is Arman. So hopefully you can see my screen here. So I wanted to pick up where Jason left off and talk a little bit more about this related concept of positivity. So you remember just from this talk here that positivity, this assumption is really lurking in the background. And so this assumption here is that we really want the probability of treatment here to be bounded for all the different levels of X. And so if there is some region of X where this doesn't hold, then the treatment effect may, if this probability is near 1, it might only be weakly identifiable because there aren't any patients in the other treatment group, and so it's difficult to actually have any data to speak to the treatment effect in that region of X. And so the reason this is an issue is because models, especially if we're using rigid parametric models, they extrapolate in those regions. So they say, okay, well, I know the treatment effect in this other region of X where I have overlap, and then maybe now I extrapolate it to a non-overlap region. And that extrapolation could be incorrect. And not only could it be incorrect, but if you have a poor extrapolation model, it might underestimate uncertainty. Right? So our posterior uncertainty about the treatment effect in these regions should be very high if there's just not enough people in one treatment group. And so the other important thing to note here about positivity is just that there's a trade-off here, especially in high dimensions between satisfying ignorability and then satisfying overlap. And typically, we want to include a lot of X's, control for as many things as we can, provided that they're not bad controls. But then if we do this, that sort of increases the chances of some overlap violation. So if we include a lot of X's, then maybe there are going to be some pockets of X where overlap does not hold. And then, and so if I've convinced you that this is important, then I think some relevant context to BCFs is how it behaves in these regions. We want to understand what is the extrapolation that Bayesian causal forests do when they encounter these regions of non-overlap. So to that end, we have this, we've presented this in the discussion paper, but it's this very stylized sort of example simulating data under some very extreme positivity violations. So here we have a lot of simulated XY pairs, just with one-dimensional X, and the color here represents treatment status. And you can see that in these gray regions of X, we have some decent overlap. So there are a lot of red patients, a lot of these black points. And then outside of these gray regions, we're running into some non-overlap, right? Because there are mostly black points outside of these gray regions. And if we run Bayesian causal forests using the very nice and fast R package that Hahn et al. Have available, you can get this estimate of tau, or the treatment effect, as a function of X. And you see that in the overlap regions in these gray areas, you have a really nice posterior estimate of the treatment effect. They're very precise. They're close to the true treatment effect that's in red. But then when you get deeper into the non-overlap regions, you see a lot of bias, and that's expected. But what I think is a little bit more concerning is that you have very narrow intervals, right? So it's being very precisely wrong. And part of this has to do with the homoscedasticity in BART, right? Because BART is a very flexible mean function, but at least the vanilla BART just sort of assumes that your errors are Gaussian and that there's one variance that governs them, and so this makes it difficult for your uncertainty to vary and increase the deeper you get into non-overlap regions, and then decrease if you're in overlap regions. And it's also non-smooth, right? You can see in this non-overlap region here, we're predicting the same value, the same treatment effect across some substantially different values of X. And this is sort of undesirable because we might believe that, well, if you have a little bit of a different X value, you should also have a little bit of a different treatment effect value. So this behavior is largely due to the step function behavior of BART. So if you use something like a Dirichlet process mixture, which is smoother, or even a Gaussian process regression, not that these methods don't have their own shortcomings, you see that the uncertainty actually varies wildly. So it increases in the non-overlap regions, it decreases in the overlap regions, and maybe this is a more desirable behavior to have as far as overlap is concerned. And I mean, so there are some options. What do you do if you have non-overlap, and when do you have it? I mean, I think non-overlap happens quite frequently if you don't have targeted selection, especially if treatments are protocol driven. All right, so even if the prognostic function indicates that a patient might or should get treatment, if the protocol recommends against it, you might have physicians who hesitate to defy this protocol, right? And that creates these pockets of non-overlap. And so one thing you could do is just sort of ignore it and run BCF, and then just be cognizant of the fact that we might be underestimating uncertainty for these people in the non-overlap regions, and to really just take the inference that we get with a grain of salt. The other thing that people might do is trimming. So maybe identify these patients and then throw them out. It's not very satisfying from a Bayesian point of view. We don't like to throw out data. Intuitively, I would think that someone in the non-overlap region, I still want to do something with them. It's just that I have a very high degree of uncertainty about it, and I want that baked into my posterior. And of course, if we're talking about average treatment effects using BART, then we're changing our estimand by trimming. There are these interesting modifications to BART, and one of the nice things I like about the BCF paper is that it sort of hints at the fact that you can maybe plug in different things for mu and tau. And what if we plugged in the smoothed BART that Linero and Yang had developed, right? And to get rid of the step function behavior that we saw in the previous figure. Or what if we use this fully non-parametric BART model developed by George and others, where instead of putting making a strong normality assumption about the residuals, we actually say, okay, they follow some unknown distribution, and we will put a Dirichlet process prior on these errors, and maybe that could actually help. But I think having a model that behaves in a desirable way in these pockets of non-overlap is maybe a good thing to think about, and maybe desirable than just ignoring or trimming from Bayesian point of view. And then I just want to say that I really enjoyed following this paper, even when it was on archive for the last few years, and seeing a few talks on it over the past few years. I think it's been a really great paper to follow. So thank you.
Thank you. Thank you, Arman, and thank you, Jason. The next invited discussion is by Georgia Papadogeorgou and Fan Li from Duke University.
Okay, can everyone see my slides?
Yes.
Okay, so actually I will do the talk, and then Georgia can correct me if I say something stupid. So it's actually very nice to follow up Arman's discussion, because I will also the overlap issue and the choice of priors is also a big issue that I'm going to talk. So since I only have 7 minutes, I try to cover 3 points. So I will talk about one conceptual point is more like a comment, and then 2 more specific points about the specific models and priors used. So the first point, so I think that this the Hahn et al. Paper is really a nice paper, and a really, to me, essential message, takeaway message from this paper is it's important when you do Bayesian causal inference to explicitly include estimated propensity score in the outcome model. So that is very important, and why this is put this message front and center is important was because to me, there was the role of propensity score in the Bayesian causal inference has been, subject to some debate. So if you read the original paper, the first paper on Bayesian causal inference, the Rubin 78 annals paper, so he first introduced this concept of ignorability. So what is ignorability? And here we assume ignorability. That means, when you have ignorability means actually you can ignore the assignment mechanism, basically the propensity score in your likelihood, in your analysis. And then later, of course, in 83, the Rosenbaum-Rubin paper about propensity score, the title is the central role of propensity score in causal inference. So in that sense, it's central. So this seemed to be a little bit conflicting, right? And then later in a Robinson advancement discussion paper in 2015, they actually also revisited this issue. They think that propensity score is really a dimension reduction, the key dimension reduction tool in high dimensions. So that's why it's important in Bayesian causal inference. So those are all this conflicting. This is the history of the debate. So I think the Hahn et al. Paper give a very nice example, actually, of insight in why actually propensity score is important in Bayesian causal inference. So we can actually this view, their idea is to again include the propensity score as an additional covariate predictor rather than the single covariate, as Rubin earlier suggested. So this is, in some sense, their method can be viewed again in a very high level as a Bayesian analog of the double robust approach. So double robust approach, if you're familiar with that, traditional statistics, it's really in weighting. It's basically combined weighting and regression. But more and more recently, like Rod Little's work and other people's work show that you can also actually, the key point is really double. It's not weighting. It's the double in the sense that you combine the propensity score and outcome modeling. And so this is basically a Bayesian analog. How I view Hahn et al. Idea, this is very similar to, it's almost like a continuous version of propensity score stratification. And then at each value, each straight or each precise value of the propensity score, you do additional outcome model. So this is, of course, their continuity or parsimony parsimony assumption going to that. But essentially, this is what's happening. You're just conducting outcome regression at the stratum of each value of PS. So in that sense, it is an analog of the double robust or double learning approach. So the nice thing of combining these two is BART, because it's a Bayesian non-parametric prior method, it provides enough flexibility to try to adjust for confounding. To adjust for confounding, and at the same time, the propensity score, in one sense, if your model is correct, if the BART is correct, then of course that's it, right? Propensity score is just this additional auxiliary summary statistic. But in case of BART is slightly misspecified, then propensity score actually gives this anchor, give you one layer of robustness protection. So I think this is also connected to the double machine learning approach. Very popular in recent very recent in high dimensions, but very recently it's very popular in the causal machine learning interface. So this is the first point about the more conceptual thing. The second point is about more specific to this specific model prior that Richard et al. Has proposed. So as Richard mentioned earlier, how do you do BART in this case? There are different ways, right? So first you can, as Jennifer did, was just put one BART to this outcome model and use the propensity score, the treatment, the treatment indicated essentially is additional covariate. Or you can all do two separate BART, basically fit one BART to each model. So Hahn et al.'s idea essentially is in between. So what they do, the prior really first force a split along the first split along the treatment, and then fit separate trees. So still sharing information between the groups. So this is kind of get the best of both. It's really in between approach. So the key idea, the key feature of this prior, again, as far as I understand, is really shrinking the Kate estimate towards homogeneity. And so then the question becomes, well, if the underlying truths really have increasing heterogeneity, the Kate is very heterogeneous, then how does this method work? Will it overshrink? So then we did a simple simulation here, very simple, just one simple covariate. So this is the result. So the dashed line here, you can see that So the dashed line is the underlying truth, and the red line is the BFC approach, and and then the other one is so the blue dot is fit the two separate models. Again, here I don't think we have the overlap issue. So this four graphs. So each one with as k increase, essentially the heterogeneity increase. So you can see that what is happening is when you have the when the heterogeneity is low, is when is the result when the underlying truth is really homogeneous. So BART is the richest method is really working very well, and it's also the low the variance is pretty low. But the trouble start to appear when your variance, when the underlying truth become the case really become heterogeneous. And this, I think, in some sense, we also see that from Arman's one of the example. So you can see as the underlying truths become more wiggled, again the Carvalho prior, this BART prior still gives you very low variance, but it's really getting the bias getting very big. So it's kind of very precisely wrong, use Arman's terminology. So we think that this is because it's happening because the model by construction, the prior by construction really shrink the K estimate towards homogeneity. So I think it would be nice actually to explore what would happen, to explore more what would happen, the ability for this to adapt this prior to adjust for more, accommodate the more heterogeneous outcome. Sorry, treatment effect. So then the last comment is really directly related to Arman's main point. It's like in causal inference, actually in most practical observational studies, really the biggest challenge is to how do you do inference? How do you derive causal inference actually in the region with lack of overlap? This is, I think in their terminology, high confounding. So you would imagine that a desirable prior would accurately reflect a captured uncertainty for according to the degree of overlap. So we know BART is really, the tree structure is really a step function. So inherently, it's basically assuming the same tree structure, step function across the covariant space, regardless the degree of overlap. And so then I did a simple simulation. Actually, this example is first was proposed by my colleague Shuja Doctor in our discussion. We just never wrote it up, so I think it's nice to put it here. So this is again a simple simulation. We only have one covariate, and let's say age, and we have two groups. So here I purposely didn't show the underlying truths, just to focus on the uncertainty measure. So you can see that here the dots are represent units from one group, one treatment group, and the other, the cross from another group. So you can see that clearly here, there's, a lot, other than in this middle area, there's a severe lack of overlap. Okay, so then we fit actually three different models. One is just a linear model. The other is use GP. I guess if you use the differential process mixture, it's probably similar, but we just use GP, another GP. And then we use BART. So we'll see, we can see that what is happening. So this is effect, the estimate effect. You can see that the linear model, again, when you have enough overlap, good overlap in this middle region, all the results doing pretty similarly, all the models doing very similarly. But then when the linear model actually, as we move away, when we get less and less overlap, you can see the linear model actually will increase the uncertainty, but it's still vastly, it seems to vastly underestimate the uncertainty. And then let's see BART. BART is really, you can see the credible band of the true effect, it just doesn't change, regardless of what's the degree of overlap. But the GP, seem to really well accommodate, well reflect the uncertainty according to the degree of overlap. Again, I'm pretty sure if I fit the DP mixture, I probably will see similar behavior as GP, because GP at different mixture has much higher, seem to be more flexible just by construction. And of course, this is just a simple example to show the point. So I think it's also similar as Arman. I think it's important actually to investigate the practical performance of BART in the region of lack of overlap, and then maybe do some can adjust it somehow to overcome this issue. And BART, again, the nice thing about BART is that computationally is really quick. So GP and the derivative mixture, I think in terms of computational time, it's probably not as good as BART. So that's what me and Georgia want to say, unless Georgia has something to add.
Perfect. Thank you, Fan, and thank you, Georgia, for contributing to the invited discussion as well. The next invited discussant is Stefan Weiger from Stanford.
Right. Let me just connect here. Oh, can I do AirPlay with this? Or is this disabled?
I'm not sure. AirPlay.
Oh, sorry. Yeah, this is all good.
Okay.
Sorry, I'm just confusing myself. All right. And so, yeah, just before I get started, I wanted to first thank Richard for the very nice talk, and also co-authors for the paper. And thanks, Michele, for inviting me to say a few words here. So, since there have already been two very nice discussions, I think I can go pretty quickly over the main setting here. This is so kind of following Jennifer Hill's 2011 paper. Bayesian non-parametric modeling has proven itself to be a very useful, and it's become a very popular tool for modeling treatment effects. And what this paper does is proposes BCF, which is essentially a variant of BART that's tailored to treatment effect estimation. So what the two previous discussants did was they commented kind of on the specifics of BART, of BCF, including the prior design. So I'm not going to revisit that here. What I wanted to do also, since kind of Bayesian methods aren't kind of at least currently in my research focuses, but what I wanted to do is kind of talk briefly about, so Richard nicely outlined some big ideas that were behind this BCF algorithm. So I wanted to kind of talk briefly about how they connect to ideas kind of in the broader machine learning for treatment effects literature, and how these ideas align. So that's what I want to do here. Before that, though, I just wanted to quickly mention, this is just a last-minute addition while the other discussants were speaking. I really liked the point you made, Richard, about simulation designs, and how good simulation design is really very important for kind of credibly validating methods for treatment heterogeneity, and how there's just a lot of crazy stuff out there, like simulation studies where the treatment effects have 100 times the range of the main effects of the noise, and you're like, no real data ever looks like that. So I just wanted to say I'm completely on the same page about that. And actually, I've had a postdoc, Eric Sverdrup, who has recently been working on kind of something very similar to what you were talking about. Just kind of here, this isn't in the GRF package yet, but we're going to ship it soon, where it's kind of a unified function for generating data from different DGPs, where exactly in the terms you were talking about, Richard, we ask you to specify how much signal is there in the noise, in the Kate function, and in the main effects. And then based on that, you can kind of build variants of different things. So I just think I really like that you brought this up. And I mean, if you want to coordinate offline on somehow how to, currently in this package, we only have collected essentially simulation designs from mostly papers I've worked on, but I'd be very happy to kind of collaborate on a broader library of this type that has kind of more representative simulation.
Sounds good.
Cool. But anyway, so this was just the last minute addition. Now going back to the slides I had actually prepared beforehand. So first something we've talked about a lot already in these discussions, so I'll go over quickly, is a first kind of big idea for designing good non-parametric methods for treatment heterogeneity that just comes up all the time is you need to avoid regularization-induced confounding. And this means you need to regularize your method, whatever you mean by regularization, in a way that pushes treatment effects towards a simplicity. Under unconfoundedness, kind of, you can write the conditional average treatment effect as a difference between two regression functions, but that doesn't mean that learning these regression functions on their own is necessarily a good idea. You can end up in all kinds of trouble. My go-to example of this type is, I'm missing the bottom of all the slides, I just realized. Sorry, this is taken from a paper by Kunzel, Saikan, Bickel, and Yu. They introduced the X learner in that paper. Here's just an example where you have a lot more control data than treated data. And just even though you're in a randomized trial, just from the fact that you have more data who are assigned treatment as 0 than 1, you end up in a situation where you fit a very complicated function to the controls because you have a lot of data, not very much, you have just a little bit of data for the treated, so you fit a very simple function to them. And then when you take a difference of these two regression functions, you end up with something very unstable and complicated, even though the treatment effect itself was constant. And like when the treatment effect is constant, any good method of treatment heterogeneity should absolutely say that the treatment effect is constant. So what can you do about it? And here, of course, there are many things one can do. Often when I cover this, say, in class when I'm teaching this, I like to use the example of the lasso because it's just very transparent, at least for people who are used to kind of penalization as a kind of first idea in high-dimensional regression. So then if you assume that your conditional response functions are linear and high-dimensional, so you need to penalize beta so as not to overfit. This means that in the high-dimensional model, tau of x is going to be x times the difference in betas. You could fit each beta on its own, but then you might suffer from regularization-induced confounding. So a very simple fix to this is, instead of regularizing beta 0 and beta 1 towards 0 on their own, regularize kind of the sum or the average of the two towards 0. That's like a main effect, and then separately regularize the difference, and that's good. And of course, what BCF does is it designs a prior that accomplishes the same thing in a Bayesian setting. And if you're familiar with the causal tree algorithm, like impins, they kind of algorithmically modify this. You get this out of trees. The X learner is kind of and virtual twins. These are kind of generic meta algorithms that you can use to kind of build this kind of idea into any machine learning procedure. So this is kind of idea number one. I think you need to do something like this if you want to get good non-parametric K estimates. The second big thing in the BCF paper was that to look at the propensity score. We know kind of by experience that in observational study methods, the propensity score is always super important. Richard Nessie highlighted the problem of targeted selection. If the propensity score is associated with baseline effects and the baseline effects are complicated, then if you don't focus on the propensity score, you could easily get biased. And what they do in the BCF paper to address this issue is that they first estimate the propensity score as a covariate and use it to model baseline effects. And I think this is a thing where kind of, at least in the past, there was some discussion about whether this was awkward to do in a subjective Bayesian setting, but kind of, I think that the evidence is pretty unambiguous that best practices for high-dimensional causal inference essentially require you to do something that's focused on the propensity score in order to avoid confounding bias. And if you don't, then you're just really vulnerable to confounding bias. So this is kind of, again, a recurring theme, and it seems like this adding pi hat to BCF as a covariate helps a lot. A third idea that's gotten quite a bit of attention in the kind of broader machine learning for treatment effect estimation community isn't as central in BCF, is this idea that, okay, you can think about treatment effects as the difference between two regression functions, But if you kind of try to model it that way, you have all kinds of problems like regularization and induced confounding. So is there something else you can do that just kind of, instead of looking at the regression loss function, looking at a different loss function and having a loss function that just directly targets the treatment effect function in a way that kind of makes it so you don't need to worry about stuff like regularization and induced confounding anymore. So this kind of idea in causal inference, I think the first paper that I'm aware of that really pushes this kind of perspective is van der Linde and Dudois in 2003, but it's entirely possible I'm missing something also. But just in this category, one simple kind of procedure that kind of directly targets the treatment effect is if the propensity score is null, you can create these transformed outcomes, delta I, and then you can check that tau of x, the condition of a treatment effect, is just the conditional expectation of delta I given x. So now you could estimate tau of x by regressing delta I on x. It's not necessarily the most powerful thing you could do, but there's no confounding from baseline effects anymore. Kind of you're just directly targeting tau of x. Other kind of more recent ideas in this family include the R learner and the DR learner that are kind of robust loss functions that again try to target the Kate function directly. So anyways, that was kind of a third idea that isn't as central as the first two in BCF, but has received some amount of attention in the broader literature. So anyways, having said that, I just wanted to close with two questions that I had, that I was thinking about while reading through this paper. So the first, and I think this is something that's been echoed in earlier talks also, is some of the loss-based methods, including the R learner and the DR learner, they essentially build on the double robustness literature, and you can prove robustness properties where these methods do rely on propensity scores, but even if the propensity score isn't known particularly accurately, you can still check that you learn the Kate function at optimal rates. Because these methods kind of are robust, they can compensate for errors in learning the propensity function via good outcome modeling. So a first thing I was wondering about is how does inaccuracy in the propensity scores, estimated propensity scores, affect BCF? And do you have conjectures about similar robustness properties? Is it possible that kind of even if the propensity scores aren't so good, they're still kind of accomplish the deconfounding task? And the other thing I was just thinking about, here we've been talking about the propensity scores really playing a central role in getting rid of confounding, and you can't avoid that. But in some cases, you might actually be interested in the propensity score as an effect modifier. For example, there's this paper, a line of work by Brandon where they ask stuff like, what is the benefit of going to college? And if the propensity score here is what is the probability of you'll attend college given your covariates, then are the people who have the high propensity scores, that is, that are the most likely a priori to go to college, or those with the low propensity scores, who are the ones who benefit the most from going to college? So here, the propensity score is an effect modifier. And what kind of results are available here or in other settings? I'm kind of talking about the relationship between the Kate and the propensity score in general. Anyways, that's what I had for now. Thanks again to Richard, the co-authors, organizers, and yeah, thank you.
Thank you again, Stefan. So we will have now the rejoinder by the authors. I think Jared will be the one who is going to present it.
Yeah, thanks, Michele. I'm going to do my screen share up here.
In the meantime, I will just say that if anybody has questions, compelling question, or wants to intervene at the end, please put the questions in the question and answer box or raise your hand.
Okay, great. Can you guys see my rejoinder slides here?
Yes.
Okay, great. Yeah, so just to double down on what Michele said, I've been trying to sort of answer the questions that people have been posing in the Q&A box there, sort of anticipating that we might run a little bit long on time. But please feel free to follow up with me, with Richard, with Carlos, with any subset of the three after the talk. Just drop us an email. We're more than happy to answer any questions that remain. We also wrote a pretty long and extensive rejoinder, perhaps to Michele's chagrin, but I think we tried to be very comprehensive with the stuff that was raised by the invited discussants here, but also the folks that went to the trouble to contribute to discussion as well. So I think that's kind of a nice synthesis. I'm really not going to have time to talk about it all here, but I'm going to focus on a handful of things. So let me just pause before I do that. And thanks again to the BA editorial board for choosing to have our paper as a discussion, and to all of our discussants, the invited discussants that presented here, and also the folks that contributed discussions for all their thoughtful comments. So there are all kinds of really great points raised by our discussants, and more than I could possibly get to if I want to stay even close to on time. So I'm just going to talk about 4, and some of these in more or less depth. I'll start out by talking about overlap issues that came up in a couple of the discussions that we saw here, and I think that our perspective on this is maybe a little bit different. The second thing I want to talk about is how to make the default BCF prior your own. We got some questions in the chat about how to actually set the BCF prior parameters. In the paper, we propose a default. We kind of arrived at those default settings through a bunch of those simulation exercises like Richard walked you through. We've gotten quite good at those over the years, but there was sort of extensive evaluation of these choices in simulation, and that's kind of how we got there. I want to talk a little bit about targeted selection. That came up in one of the discussions here, and just want to make some brief comments about that. And then finally, I'm going to come back and talk about revisiting the role of the propensity score, all the different ways the propensity score seems to matter and comes up in practice. Before I do that, I want to make sure that we put down a marker for BCF 2.0, which is not quite on CRAN, but it is production ready. I just need to clean up some little bits and pieces before they'll accept it and post it. We have lots of nice new features in BCF 2.0. There's parallel computing, saving fits across different sessions, R sessions to generate predictions of treatment effects without starting from scratch, some MCMC diagnostics, new vignettes, and a lot of other good stuff. Almost none of that is due to me. That is courtesy of Marielle Finucane, Peter, Constance, and Lauren, who I think at least some of you guys were here. Thank you all so much. Hopefully I didn't forget anybody on the team, but I tried to get all the contributors there. So thanks so much to them. And if you're interested in using BCF, head right over to the GitHub and try that out. Okay, so I want to start by talking about lack of overlap and what we should do about it. I don't know if Fan is still here. I know she had to run, but I really like this example that she and Georgia presented, which I guess is sort of by way of Sharia, which I didn't catch in their write-up. But a nice little example here of where we have a lack of overlap. So she talked you through this plot. It's the same one that you're looking at here. In the discussion, they sort of make the comment that BART in the linear model are overconfident relative to the Gaussian process. And, I guess that's just sort of based on the rank order of the uncertainty when we have pink outcomes. I think those are the treated outcomes that are in higher ages. Blue outcomes, I think those are the control outcomes at lower ages. We'll try this pen. I don't know if this works. It does not. Okay, that's fine. And so, when I was reading that discussion, I was thinking to myself, who really is overconfident when the overlap is poor or non-existent, right? At the very high ages, at the very low ages. And, I think our answer is that everybody is overconfident, right? When we don't have overlap, treatment effects are not identified. And in a very real sense, the appropriate interval width is infinity because we just don't know and the data can't tell us, right? The only case in which we can think about trying to make inference outside of there is when our model is using real prior information to extrapolate because the data just can't tell us what's going on, right? That sounds like a pithy little comment, but it's real, right? If the thing that we're trying to estimate is not identified, then all we're doing is sort of extrapolating out based on a model, and I think that's a little bit fraught. So why do I think that? Well, I sort of went back and I looked at the discussion that Fan and Georgia contributed, and I just superimposed approximately what the True expected outcomes are under treatment and control, under their data generating process. If you looked at the pictures, you probably suspected it was linear, and in fact it was, right? So I just kind of dropped some red lines there about where the true linear functions are. And it turns out that the linear model was doing great because the truth was linear. The Gaussian process, once we get past the areas where we have data, the intervals are large, but they don't capture the truth, right? So there's some question of whether the Gaussian process is not also overconfident. I think it is. And then, of course, BART misses as well, right? Because they're extrapolating in different ways, but neither one is extrapolating in the correct way, okay? So I just think that obtaining identification solely on how a black box model is going to extrapolate, it's just a bad idea. You're going to be right when you're right, you're going to be wrong when you're not, and there's just nothing you can do about it. And I wanted to point out too that here, even the Gaussian process, the mean of the Gaussian process, the prior is actually centered at the correct functional form, a linear function in age, and we still get these sort of weird little, they're not weird, I mean, it's sort of obvious what's happening here, right? We get these ticks up for the pink curve and a tick down for the blue curve, just kind of based on those extremal data points, right? And that's just how Gaussian processes extrapolate. I'll come back in a second and talk about the BART extrapolations as well. So I don't want to try to estimate Kates or ITEs out here in this region where I don't have overlap. If we drill down to the area where we actually have what I would call practical overlap, so sort of visually here, I'm just kind of identifying that as regions of covariate space where we actually have treated and control cases, we get a little bit more nuanced picture of what's going on maybe. And then if we drill down even further and actually sort of take out that middle where overlap is good and kind of focus on where we have poor overlap, we have relatively few treated or control cases, you see kind of an interesting picture emerge. I'm going to blow this up like I'm a tech on CSI. Unfortunately, unlike CSI, I just have a poor resolution image, so I apologize for the fuzz. But what we see in this picture is that once we start getting into areas where we have overlap, we have practical overlap, depending on how you define that, the behavior of the Gaussian process in BART, it's a little bit different than what we saw in the extremal region where we didn't have overlap at all. So in particular, that Gaussian process that assumes those functions are super smooth is actually going to be slower to adapt to having larger intervals than BART, right? The Gaussian process is a smoother prior than BART, so it's going to extrapolate more smoothly. And as we sort of approach that region where there's not overlap, the intervals aren't going to get as wide as fast. Again, that's not to say the Gaussian process is bad or that BART is good or vice versa. They're just different priors and they're going to behave in different ways. I want to say a few words about how BART extrapolates here because I think there's actually some confusion about that. So BART model uncertainty does increase of places where we have no overlap or places where we have poor overlap, right? That's sort of obvious from this picture. Some people think that it doesn't increase at all, but it does. You see the picture. And in fact, this actually came up in the chat. This increase of uncertainty between the expected outcomes under treatment and the expected outcomes under control, the increased model uncertainty about those parameters, can actually form the basis for a diagnostic for lack of overlap or for poor overlap. And that's this Hill and Su paper in AOAS. A really nice paper. That's like a general strategy we could use to identify areas of poor overlap. The same thing is true for BCF. So these narrow intervals here, they're not just because BART is based on trees, they're also due to sort of a key feature of the BART prior. The BART prior, Richard talked about the process prior as we grow that tree down in a BART ensemble. One of the rules that we have when we grow that BART prior down is that we will automatically reject any splits that lead to empty leaves, okay? That's not necessary. You can define a well-posed tree process prior that will keep growing into areas where there actually is no data. And if you did that, you would see these intervals out here in the area where you don't have overlap. You would see them continue to get bigger and then eventually approach the width of the prior standard deviation on the function evaluations, okay? So that's just to say, there's a very particular reason in that prior that uncertainty doesn't increase out there. And it's a feature, not a bug. My conjecture, I don't have a lot of proof for this, but my conjecture is that kind of data adaptivity is one of the reasons that BART works so well in prediction and causal inference, where you actually do have data, okay? So you could tweak that prior to make these intervals get a little bit bigger. I don't think that's actually the fix, right? I don't think it's a good idea to be estimating Kates where we don't actually have overlap just because they're not identified, unless we're willing to try a little bit harder, okay? So what do I mean about that? So what are we going to do? So there are a few things that we can do. One would be to identify regions of poor or no overlap and just avoid estimating case there. Jason and Arman referred to this as trimming. If you do that before you estimate your model, I mean, there's nothing anti-Bayesian about it. So we'll come back to this in a second here, but when I'm doing Bayesian inference, I'm conditioning on realized treatment values and realized covariate values, okay? And I'm determining where I have overlap or I don't, just sort of based on those. So there's nothing anti-Bayesian about the trimming. You also don't need to do the trimming before you fit the model. You can fit the model and then just restrict your inferences to the area where you have overlap. On the other hand, I totally agree that there are cases where we might want to try to estimate treatment effects in areas where we have poor or no overlap. And then the question becomes, what do we do? Whatever we do, I think we need to do it carefully. And the way that I would think about this problem is formally thinking about it as a problem of partial identification or just complete non-identification, depending on what you're willing to assume about that function. I think that you need to bring real prior information to the table. I don't just mean generic statements about smoothness, but actual sort of patterns. So smoothness, shape, range of the treatment effects in the region where you don't have overlap. If you can't bring that to bear, I just really don't think that you can learn much. And in particular, I think you need to be conducting sensitivity analysis with respect to items 1 and 2 here, how you define that region of no or poor overlap, and then how you think about building that extrapolator. There are a lot of different decisions you could make. And at the end of the day, your data aren't going to be able to tell you if you're doing a good job or if you're doing a bad job. Okay, and this is sort of an approach that we've brought to bear before. It's related to a lot of other ideas. I saw as people were filtering in, I saw we had Paul Gustafson. I don't know if he's still in here, but he's sort of a long-time thinker about this. Lots of great papers, lots of great, and a great textbook too for Bayesian approaches to non or partial identification. I guess this is all easier said than done, but learning about things that are unidentified by our data is just hard. And I don't think there's a model out there that's going to save us. Okay, adjusting the BCF prior. So like I said, we came up with a default prior based on a bunch of iteration and a bunch of simulations under scenarios we thought were reasonable. It's not going to work well everywhere, okay? We saw in Fan and George's discussion a case where we were maybe over-shrinking. So the plot over here on the right is one of the scenarios that they presented in the discussion, where we have this sort of highly oscillating function here. We have a relatively small sample size, and the blue in their picture is the separate regressions estimate of treatment effects. The red is a BCF estimate of treatment effects, and the black dashed line is the truth. That's in their picture. I don't think you guys can see my pointer, but I'm waving it around anyway. And then over here on the left, I have 3 plots under 3 different BCF priors where I've just gone ahead and relaxed the default to allow the treatment effect function to be more complex, or to allow the potential for the estimated treatment function to be more complex. So on the far left is our default prior, and yeah, it kind of seems like it's over shrinking, right? It's a little bit flat where maybe you want it to kind of capture some of those peaks and valleys of the sine function. But just looking at 2 knobs we have to allow us to estimate more complicated treatment effect heterogeneity functions. The first one that I turned was I just turned up the number of trees, okay? So approximating a sine function, particularly one that's oscillating frequently with step functions is going to be a challenge, obviously. One thing you can do is allow the step function to be more complex by adding a bunch of trees. So that's the first thing I do is I go from 50 trees to 200 trees. And you can see that the estimates improve, right? The peaks are a little bit closer in the estimate, and the peaks in the estimated function are a little bit closer to the peaks in the true function, and same with the values. We can go a little bit further and vary this alpha parameter, which if you remember all the way back to when Richard showed you the process prior, that alpha is just the probability that a tree splits the first time. So by taking that up, by increasing that, you're sort of putting higher probability on trees that split at least once. And if you do that, you can actually see that the function gets a little bit closer to the truth as well, okay? And at the same time, there's this trade-off, right? The intervals are getting wider as we go because we are applying less regularization. So George and Fan, they call this homogeneity-induced bias. I like that. Unfortunately, bias is a loaded term. Another way to think about this is just prior regularization. So if your prior is regularizing in the direction of the truth, that's going to be great. If it's regularizing away from the direction of the truth, you're going to have a bad time, right? That's just sort of a generic statement. The nice thing about BCF and using the treatment effect parameterization is you can actually control that. If you think you're in a scenario where you have treatment effects that are oscillating wildly like this, that are super smooth, you can go ahead and relax the default BCF prior. We don't expect it to work well for every data generating process you could cook up. It's the one that seems to work best relative to the data generating processes that we feel like we're encountering in our own work and that are kind of running around out there more generally. But I will say that when we do our own applied work, we tend to not use the default prior. We tend to think a little bit carefully about the context and what's going on, and maybe adapt that accordingly if it's appropriate. Is targeted selection plausible? This was a comment in Jason and Arman's discussion that I think we wanted to respond to. So they sort of made the claim that optimally decisions about treatment would be made based on predicted treatment effects. And I don't think that's quite right. Thinking like a Bayesian, I would make my optimal treatment decision based on a probability distribution over expected outcomes under each alternative. So that's going to involve expected outcomes under baseline and also expected outcomes under treatment, right? So I think it should involve both things, ideally. And just a simple example of why we think that, if we expect for a person that a drug is going to reduce their blood pressure by, say, 100 points, it actually matters whether the blood pressure at baseline is 150 or 250, depending on whether we're trying to help them or kill them. When we sort of sat down and started thinking about targeted selection and whether it was plausible, I think the reference point for me at least was thinking about the situation where we're sitting in a doctor's office and maybe the doctor is recommending some treatment for us. I think oftentimes that decision is based on sort of a vague notion that this treatment works based on RCTs, maybe not a detailed assessment of treatment effect heterogeneity, because I think that's missing for a lot of things that are out there in practice. But we probably have more detailed knowledge of risk factors for adverse outcomes, right? So I think this is running around out there in the wild. I think it's maybe a little bit more common. But yes, ideally we would be making treatment decisions based on good knowledge of expected outcomes under each alternative. Okay, so coming back to what I'll call the still central role of the propensity score. I'll try to do this quickly because I think a lot of this stuff has come up and there's maybe a little bit less controversy now than there was X years ago when we started talking about this. So I'll start by thinking about incorporating an approximate propensity score into our priors. I want to call out Stefan's discussion, which I thought was just an excellent review and summary and kind of a look forward of all the different ways that the propensity score has proven to be important. It's one of those things that you read and you're sort of jealous that you didn't write it once you're done. I think I would say that very little controversy remains about the utility of using an estimated or approximate propensity score in your models, unless you're a Bayesian or unless you're playing Bayesian devil's advocate. I still sort of see this. So I thought it was useful to maybe go over the argument again for why we think this is okay. I think the issue here comes down to thinking about uncertainty about pi, and in particular whether pi is a parameter in our model, or about pi hat as a prior parameter. So I'll start with two sort of stylized facts that I think, not stylized facts, two actual facts that Fan also mentioned. So under conditional ignorability, a Bayesian is not obligated to model selection into treatment, right? That's just a fact. In reality, nobody is, right? We can get all the way to treatment effect estimates in principle just based on outcome models. What that means for a Bayesian is that our priors, our models, and our inferences, they can all be conditional on realized covariates and realized treatment assignments. Okay? We're conditioning on all that stuff. Whether or not we actually include it on the right-hand bar when we write down our priors, we're effectively conditioning on all that stuff. Okay. The other fact that I think we've demonstrated pretty convincingly through extensive simulations is that if the prior is furnishing non-trivial regularization, it's really easy to write down a crappy prior for the expected outcomes under treatment and control, or the conditional expectation given Z and X rather. Okay, and again, this is a regularization issue. It's not strictly a Bayesian inference issue, but once we start thinking about estimation in high dimensions or being non-parametric about it, our prior is going to be supplying non-trivial regularization. So the kind of the theme here, thinking about when we can get in trouble, the idea here is that if your prior on f of x and z is regularizing variation in the direction of pi more strongly than variation kind of in the direction of z, you're going to get confused and you're going to misattribute confounding effects to true confounding effects to spurious treatment effects. Okay. But let's think through what that means. So you might read that statement and you think, okay, so now what I need to do is I need to actually include pi as a parameter in my output model, right? Maybe I need to write down f of x, comma z, comma pi of x, where pi here is the true propensity score. And then maybe I need to give pi of x a prior of its own because I actually don't know what it is. And I think that's wrong, right? Because what's going on here is not that conditional expectation actually depending on pi of x. Thinking mechanistically, thinking about the actual data generating process, realistically what's going on, thinking about the science, like having a different propensity score is not causing us to have different outcomes, right? that variation in the direction of pi, it's happening through other mechanisms. It could be targeted selection. We think that's plausible, although not always there. It can happen by chance. It can happen due to sort of various functional form considerations about linear models. So we get into that in the rejoinder. So I don't think that you're obligated to have the true propensity score in there as a parameter. Okay. But now let me sort of square that circle about why that's sort of looks like what we actually do, where we add pi hat of x as an argument to either f, if you're doing a propensity score BART like we proposed, or into this function mu if you're fitting BCF. The hats here are important, right? So one way to think about this is just as shorthand for actually trying to change the prior on f or trying to change the prior on mu. So in the context of tree priors on f and mu, what we're doing here is we're just saying that we're going to let those trees split along an axis defined by pi hat of x. And we get to pick that axis the same way that we picked the coordinate space for x and z. Okay. So really what we want to think about is we want to think about that pi hat as just a parameter of the prior on f or u. It's something that we get to pick in the prior. Remember that prior already is conditional on x and z. And you know, the fact that we write it here as an argument to the function is not to sort of suggest that our model is saying that the actual estimated propensity score is driving outcomes, or the true propensity score is driving outcomes. So this is not sort of a plug-in approximation to having the true pi in there, if that makes sense. And so once you start thinking about it that way, once you think about pi hat of x as just a way that we are defining our prior, really we should think about it like all the other choices that we make when we pick a prior. So in particular, like the other choices we make when we're setting our priors, it's subject to criticism and ideally sensitivity analysis, right? Stefan asked the question, what happens if pi hat is not a great estimate? A related question is, what if we have different estimates pi hat and we're not sure which one is the best? Sensitivity analysis seems like a good idea here. Like any other parameter in our priors, we're not obligated to give it a further hyperprior just because we don't know exactly what it is, because we might have made a different choice, or because we might have made a different choice if we saw different x's and z's, right? The analogy that we make in the paper is the analogy to Zellner's G prior, which depends on x transpose x. It's not obligated to think about the true covariant structure of x because all the inference is conditional on the covariance that you actually saw. Okay. So just a couple of other propensity score comments, questions that came up. Stefan raised the question of the approximate or the actual propensity score as a treatment effect moderator. I think including an estimated propensity score in tau in the BCF parameterization, it makes a ton of sense, right? It definitely could improve estimation when selection into treatment is determined by what people think their individual treatment effects are going to be. The reason that we don't do it in BCF is that it can actually degrade the mixing when you're trying to sample from the posterior for tau. It also complicates interpretation a little bit if you want to think about, you know, if you want to try to use your estimates to do something like get a handle on sort of partial effects of one treatment effect moderator on estimated treatment effects of the others. It's a little bit of a finer point. But either way, whether or not you actually include an estimated or actual propensity score in that function tau, you can always get your estimated treatment effects and sort of plot them or otherwise investigate them as a function of the propensity score. I think that's a useful thing to do in a lot of contexts. We might have questions about whether the people that actually benefit from treatment are the ones that are getting it at higher rates. Another question was about including the estimated versus the true propensity score. So there are scenarios where the estimated propensity score is just about as good as the true propensity score. You know, in simulations, we see better results using the true propensity score. That seems to hold pretty broadly. The gap is not always huge. It really just seems to come down to how well you estimate that propensity score, how close pi hat is to pi. What we find empirically is that it doesn't need to be all that close. But I would say that we don't have a deep understanding of this, theoretically, for sure, or what the gap is in practice. You know, I would love to see some of the folks that are doing more statistical theory take a sort of aim their cannons at BCF and related models, because I think there's a lot we could learn from that. But yeah, this is what we see in simulations and kind of the intuition there. Okay, I'm over time, I think, so I will stop here so we have a little bit of time to answer questions. Thank you all again.
Perfect. Thank you so much. Thank you so much, Jared. Yes, we are a bit over time, but on the other hand, I really feel that these discussion papers represent an occasion for, you know, stimulating discussion among people. So I've seen that Richard, similarly to GR before, has been answering some questions already online. we are reduced to a few now of attendance with respect to the beginning, but if anybody has some important, relevant questions to ask still, please, could you raise your hand so I can give you quickly the possibility to talk and ask a question directly? Let's see. I don't see any hand so far raising up. Probably that means that we have been, oh, let's see. Oh, one, Jacob. Okay, go ahead.
All right, can you hear me?
Yes.
Cool. So that was great. You know, it's almost 2 hours now. I took about 4 pages of notes, and as with everything in causal inference, the considerations and the justifications of your assumptions is very, very, very complex. And I'm just always wondering how do you expect practitioners to grasp all this complexity and then also have a effective conversation about this? Do you have any ideas how we could make this more effective, more accessible? Because I always think like putting up a GitHub package is great as a first step, but sometimes it can also be a bit raising the expectations too high in the sense that you just download it, you run your data, and there you go. So how can we facilitate better access to understanding how the methods work? Because oftentimes practitioners don't have the time to read all the papers and the literature of Bayesian statistics and so forth. Do you have any ideas on that?
So, I mean, in some sense, your question is about education. It's about educating practitioners about causal inference. So I have been teaching causal inference class for, I guess, 3 or 4 years now, sort of introductory graduate level. And, you know, as you might imagine, based on what I've said already, like I really think understanding and seeing this stuff in practice via simulations is one way to help people internalize the ideas of confounding and non-overlap and how an instrument works and all these other things. And without concrete examples like that you can sort of see in action, I think it's hard. In terms of like making that a resource, it's a good suggestion. I think it'll take a lot of work, but yeah, there needs to be more educational outreach. I agree that putting an R package up or a Python package is sort of preaching to the choir. Other methodologists are going to be more apt to use it than practitioners. On the other hand, you know, I don't know that people really understand linear regression who use it all the time. And I would much rather they use BCF than OLS when fitting these models, because it seems to work better on a wider range of things. So it goes both ways, I guess. But you're right, it's a delicate topic, and figuring out how to broadcast it is a challenge. Videos, stuff like this, maybe workshops, Michele.
Great, thank you. So we have a couple of questions. One from Haleha. Is it possible to estimate marginal structural models with BCF?
I'm going to let Jared answer that.
Maybe. So I know Jason has a paper doing this with not BCF, but a similar model. It is probably possible in principle, but I'm not sure how you would do it offhand.
Okay. Ali is following up to a previous question that Richard has already replied to, and is asking, I wonder how one can propagate the uncertainty due to the estimated propensity scores in the posterior predicted draws of the outcome in BART.
So how do we propagate the uncertainty in the propensity score? We don't. We don't want to, we don't need to, we don't claim to. If you think you have a bunch of candidate ones, like Jared mentioned, you can test them in a sensitivity analysis. I would add to that one thing that you can do, like let's say you've got 5 different estimates or even 100, you could actually throw them all in the way that we're currently doing now and provide all of them as directions to search for BART. That's actually my preferred way to do it. So if you've got a couple of different candidates, in particular, what I would do, throwing this out there, haven't written this paper yet. So you fit a Bayesian model, you take 10 posterior samples that are at sort of a wide range, you drop those in as 10 new columns to your X matrix, and then you run BCF. So it's not propagating the uncertainty in the traditional way.
In addition to pi-hat, right?
In addition to pi-hat. Well, these are all pi-hats, right? It's pi-hat 1.
The posterior mean, yeah. So I think
sure.
So Richard and I have actually riffed on this before. So I think I hope we agree. But I think the issue with, like, if you just wrote down a Bayesian propensity score model and you got a couple of posterior draws for pi and plugged them in, one thing that you run into pretty quickly is the fact that each individual draw might not actually be that great an estimate of pi, right? So if you're just using each one of those, or even if you're using all 10 of them, that's not going to work as well as having one really good estimate for the propensity score. But if you want to add a little bit of fuzz, I think using the draws is reasonable.
Yeah. But anyway, like the joint, we talk about, we have our rejoinder is like 19 pages long. And one of the things we talk about is exactly this. We feel strongly that you're not obliged to model that. And therefore the uncertainty is really a matter of prior uncertainty, which if you think about it, like what is prior uncertainty? Turtles all the way down, I guess.
Perfect. So what I will do, so there is still a question that maybe I'll ask, if possible, Richard or Jared to reply to in the chat textually. I think we are at the mark of a second hour, so probably it's the time to stop. So I apologize for remaining questions. The talk will be available on YouTube. I will upload it later today, so you can follow again the seminar, the webinar there. I will also upload the questions. I saved them and the answers. I just wanted to thank again Richard and Jared to participate to this discussion paper, and the discussant, Arman, Jason, Georgia, Fan, and Stefan for their insightful comments. And I will finish just reminding that there is an open contribution call for the discussion paper in December, which is on a class of objective prior from scoring rules by Fabrizio Leisen, Cristiano Villa, and Stephen Walker. We're waiting for contributed discussion before November 3rd. Thank you again, and great. I think this was fantastic.
Thanks, everybody.
Thank you.
A lot.